In this practical, what we're going to do is have a look at Ohm's law, and in particular, we're going to find the relationship between potential difference, measured in volts, across two different conductors or resistors. The first is this globe here, and the second is this resistor here, which you'll see in close-up in a little while. So we've got the incandescent globe and we've got the gold resistor. And what we're going to do is compare the resistance of both of these resistors. What we should expect, theoretically, is that as we increase the voltage, the potential difference measured in volts, the current should increase in the same ratio, in the same proportion. And what that means is that the ratio of the potential difference to the current is a constant. And that was the conclusion of Ohm, and that is his law, Ohm's law, that the ratio of the potential difference to the current in a conductor is a constant value, and we call that the resistance. Well, we're going to explore that, as I say, with the incandescent globe and with this second resistor. So this is the equipment here, and you can see that what we've got is a power supply, and what we've got here is a knob which enables me to adjust the potential difference between these 2 points and across the incandescent globe there. We've got two multimeters set up here, one to measure the current, and this is the one which is going to measure the current in amps or amperes, and this one here measures the potential difference in volts. And you might notice how the multimeters are set up, connected differently. So this is the circuit diagram here, and you can see there that the ammeter is in series and the voltmeter is in parallel. So we can start this by turning this on. Now you'll notice that this is set to 2. This reading on the power pack is not necessarily the most accurate one. Down here, which is a measure of the potential difference, this is more accurate. So this is our first reading, a reading where the potential difference is approximately 1.95 volts, and the current is 0.6. Now it's going to fluctuate a little bit there, probably 0.62. So I'll adjust this, and this will be around about 4 now. And what I want you to notice is what happens here to the light globe. So that obviously gets hotter and hotter as I adjust the potential difference. So now the potential difference is 3.57. We'll go 7, and over here the current is 0.84. So I'll adjust the potential difference again, and this time again we can see the globe heats up or lights up even further, and the potential difference there is 5.33, and the current is 1.03. Changing the resistance again, we've got there approximately 8 volts, but again you'll notice the difference between the two down here, and that figure is 7.32. And over here 1.22. So we adjust that still further, and now it's not 10 here, but it's 9.1. Can't make up its mind. 9.3. Let's go 9.3, 9.3. Over here, 1.3, fluctuating a bit there, but let's go 1.39. And our last reading is this, approximately 12, so that says 11.26, 11.26, and over here a current of 1.54 amps. So those are the readings for the globe. Let's have a look now at the other resistor. So now I've got this set up with the what's called the higher power gold resistor, and we can compare that now with the incandescent globe. So you can see here with no current going through it, no potential difference across the resistor. So there's our resistor there. We've got no current and a measure of 0, 0. So that's our first reading. If I turn that on, we get now a reading of a potential difference of 2.1. You can see it's changing. Well, let's say 2.2, and over here a current of 0.16. I change the voltage again and bring that up to, let's see where it gets to. Okay, let's take that as 3.7, and our current as 0.29. We adjust the voltage again, and we've got a potential difference across there now of 5.63 and a current of 0.45. Adjusting our potential difference again, 7.55 and 0.61, and it's reading 10 here, but down here, as we can see in a more accurate reading, we've got 9.4 or 9.9, let's say 9.5. Over here, let's say we've got 0.77. That seems to be reasonably constant. And this last one then is 11.5. 11.56. Okay, let's say 6. And over here, 0.93. So now we're in a position to draw a couple of graphs. Let's do that. So here we have our results. Let's look first of all at the gold-coloured resistor. And what we notice here, once we include the values of 0, 0 for the current and the potential difference, and we create our graph, what we get is a straight line. And if we have a look at that gradient, what we find is that it has a value of 12.4. That means that the resistance of this resistor is constant, and we would say that it has a resistance of 12.4 ohms. We can see that this obeys Ohm's law. That is, that the ratio of the voltage or the potential difference to the current is a constant. Let's go back over here now and have a look at the resistance of the light globe. And what we notice here is that the gradient of this line changes as the voltage is increased. What we notice is that the value of the resistance, the gradient of this line, increases as the voltage or potential difference is increased. Why might that be the case? Well, the obvious answer is that the globe is heating up. The molecules or the atoms inside the tungsten element would be vibrating more rapidly, and that interferes with the flow of the electrons. This resistor would be known as a non-ohmic resistor. It does not obey Ohm's law. So this is what we have learnt in this experiment, that we have confirmed Ohm's law applying to one conductor. We have discovered that there is such a thing as a non-ohmic conductor. And why might that not confirm with, and why might that not conform to Ohm's law? Well, it would seem that the reason is that the globe heats up and as a result offers more resistance.